Yeah, good afternoon, everyone. My name is Linfei. So currently, I'm just a new assistant research professor at University of Maine. So today, it's my honor to give you guys a presentation talking about the improving the ultra high performance concrete properties by the well-dispersed carbon nanofibers. So this is the work I've been done probably, like half years ago at CU Boulder. So at that time I was a postdoc over there. So that's why I put the affiliation of CU Boulder here. Oops, next slide. Okay, so at the beginning of the presentation, I will give you a brief outline. So mention everything I'm going to talk today. So the first part is an introduction, give you some brief idea what are UHPC and carbon nanofibers, but I think most of you are very familiar with that. And the motivation or the objective, why we want to combine these two together. So third one is we started the research work. We made a preliminary UHPC mix design selection, and then we talked briefly about the carbon nanofibers dispersion technologies we provided. And then since we after figure out the dispersion technology, we did some parametric analysis trying to make a comparison between different variables in the mix. And finally, we made a direct comparison with a pure UHPC sample, talking about the mechanical properties, workability, and permeability stuff. So let's first introduce a little bit about the introduction side. So the UHPC actually was normally produced without any coarse aggregate. So it was made by sand, cement, silica fume, water, and super plasticizer, and kind of different types of fibers, but most of them are steel fibers. So compared to the regular concrete, it can provide extremely high compressive strength as well as a trustable low permeability. Currently, there are already a lot of UHPC infrastructures have been applied in the real world. So the structure between conventional concrete and UHPC is different, and the UHPC is definitely a denser material than conventional concrete. However, even for the UHPC, there are still some macro scale, or we call even nanoscale spaces among different compositions. So it allows us to fill these spaces with macroparticles, nanoparticles, or we can call nanofibers. So furthermore, due to the low flexural strength of UHPC, the fibers are commonly added into the UHPC. So by combining these two concerns, our research team believe the carbon nanofibers will be a good fit to further improve the mechanical properties and durability. So on the other side, the carbon nanofibers have a pretty extraordinary tensile strengths and also fantastic elastomodulars. So as I mentioned a little bit earlier, so from the mechanics point, macro mechanics point of view, the composites of UHPC carbon nanofibers can actually help to develop super strong material if a good dispersion of carbon nanofibers can be achieved. Although there are many successful stories of combining cementitious material with carbon nanomaterials together, such as like cementitious material with carbon nanofibers, carbon nanotubes, and recently some with some cellulose nanofibers, but not much study right now focus on the UHPC with carbon nanofibers. So the nano-level UHPC research is still missing. In addition, hundreds of dispersion methods can be found from previous published work talking about adding nanomaterials in the cementitious materials. But right now, there is no clear trend that can let the researchers to follow, which can deliver well dispersion of the nanomaterials. So in this case, we decide to conduct a pretty comprehensive study along this direction. So the first step will be do some screening work on the UHPC mix design. So we pick up like 5 different UHPC mix design from the already published work. So and then we run the pre-decom test, the SLAM test, and compression test, trying to figure out to pick up the best one to keep moving forward. So from the testing result, as you can see, the seems like number 5 will be the one which can provide the highest compressive strength at the same time with a pretty good slump. And then the next step, we're going to talk about the dispersion of carbon nanofibers. So the agglomeration of the nanomaterial blocks the way to apply the nanomaterials in cement area, as I mentioned earlier. So as you can see, the carbon nanofibers agglomeration in the SEM figure. So from the length scale, this is definitely not a single fiber. This is kind of like a lot of carbon nanofibers bundled together. This issue could cause a sad effect actually to the cementitious material. So two major challenges for a well dispersion of carbon nanofibers have been provided. One thing is about the hydrophobic surface property of the carbon nanofibers, which could be relieved by adding some chemical surfactants, trying to change the surface properties of that. The other one is actually the van der Waals forces between different single fibers. This might be avoided with some specific treatments, like with a very powerful mixing procedure. So the table on the right-hand side showed different dispersion techniques we offered. Generally, they are the combination of different types of the chemical surfactant or different mixing process, such as like premixing from different devices or any ultrasonic dispersion process. So we use the flexural test result and the porosity measuring to evaluate how the carbon nanofibers can be well dispersed. So the flexural test results we use here to or following actually the ASTM standard C348. And the porosity measuring basically can show how the carbon nanofibers can be well dispersed and can fill the porous media. So from the testing result, as one can see, in addition to use a hydrogen water reducer as a chemical surfactant, and by using the mesocellulose and the polyacrylic acid, these are the other two types of the chemical surfactant, which are pretty common to be used. So they were not very helpful for the dispersion of carbon nanofibers based on our testing results. And same time, it can also decrease the mechanical performance and also increase porosity. So the testing result actually D10 the product D10 provided the largest flexural stress and strain as well as lowest porosity. So from the results, we decided to pick up D10 as a best dispersion technology. We also evaluate the dispersion of carbon nanofibers by using SEM analysis with the EDS. So this is like a pretty common one, like without any dispersion process, basically you can capture some very big fibers actually bounded by a lot of different carbon nanofibers. So the EDS analysis shows this is really a carbon nanofiber compared to the other side of the cementitious material. And on the other side, I talk about the well dispersion. So we do capture the well dispersed fiber, like the single fiber between the cracks, and also we use EDS analysis to prove what we have found. The next step, we did some parametric analysis. So the first thing we consider here is about like different times of the ultrasonic dispersion time. So as you can see, it seems like the 10 minutes of ultrasonic dispersion time is the best one compared to the shorter time. The reason we didn't go even longer, like to 15 minutes or 20 minutes, is because we're kind of worried about the heating generated from the ultrasonic dispersion process, because it's going to cause the evaporation of the water, which can change the mixing properties. And the second one we consider here is about different amount of the high range water reducer we use for dispersion and mixing. So from the previous test, we use high range water reducer to carbon nanofibers with a ratio of 5, and then we try to stretch that to 10. So basically, from the testing result evaluated by the flexural test flexural strength and also the porosity. We know the probably the best proportion between the hydrogen wall reducer used for dispersion to the carbon nanofibers will be like between 5 to 10, because 5 give us the best stress, but 10 give us the best strain. And the next one is about different dosages of the carbon nanofibers involved in the mix. We started from 0.05 cement weight percent and up to 0.5 cement weight percent. So same thing from the testing result, we know 0.1 cement weight percent is actually a critical value of the carbon nanofibers can be added based on the dispersion technology we developed. And now we move. Finally, we can move to the last chapter about make a comparison with a regular UHPC. So the first one we did is about the mechanical properties. So we ran the compression test at 7 days and 20 days, and also the flexural test. Excuse me. As you can see, there's not a big improvement on the compressive strength side, but we do capture a big difference on the flexural stress and the flexural strain. So which means the carbon nanofibers did make a improvement on the flexural strength or ductility of the material. And also the next one we test is a slump test. Yeah, it's pretty obvious, like when you add some very fine particles, especially carbon nanofibers, the slump decreased, but it's in a very limited range. It just decreased like from 24 centimeters to 22.8 centimeters. So which is, I think it's a pretty controlled range. And also we also did the material test. We capture like actually adding the carbon nanofibers is going to retard the hydration process. So this is actually kind of like different from the classic nucleation effect, but we kind of explain this kind of issue by the retardation from the hydrogen water reducer actually. And the last one is about permeability. So here we conducted the wick test and also the chloride pounding test for 3 months. So from the testing results, it can be pretty obviously to capture that the water permeability and also the chloride concentration will be decreased since you add the carbon nanofibers into the UHPC mix. On conclusions of this presentation, so the first step, we optimize the UHPC mix design with highest compressive strength of 135 megapascal at 28 days, and also largest slump of 24 centimeters. And then we provided different dispersion technologies of carbon nanofibers in UHPC and also made a comparison. So the amounts and types of the chemical surfactants were compared, and also the parametric analysis considered the optimal carbon nanofibers amount and also optimal dispersion time. So after we delivered we called the optimized UHPC carbon nanofibers composites, the mechanical properties, the workabilities, and also permeabilities were studied. That actually the flexural performance can be increased with no impact on the compressive strength, like 10% decrease of the slump was captured, and also around like only 10 minutes retardation of hydration was obtained. Finally, the water permeability and chloride permeability were efficiently dropped because of the involvement of carbon nanofibers. Finally, I would like to say thank you to our funding agencies, U.S. Department for Energy, for providing infinite support for this project. So, because this is only a short presentation, so there are a lot of details was not covered in this presentation. So, if you have any interest about this work, you can check the paper we recently published. And thank you very much. And we're happy to answer any questions and also get some feedback, some suggestions. And furthermore, if you want to talk to me more or maybe do some collaboration work, you are very welcome to contact me by email. Thank you.